then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, Precalculus students, and welcome to lesson number 9. Today's lesson is all about a concept called limits. Now, you may not have heard of limits before, and limits is actually covered at the end of your pre-cal book, and it's kind of the bridge between pre-calculus and calculus. And it's probably more of a calculus concept than it is a pre-calculus concept, but it is something that is taught in pre-cal. However, I just want to remind you, you're an honors pre-cal, and in our honors pre-calculus course, we're going to cover close to half of the calculus curriculum. So in honors pre-cal, we cover all of the pre-calculus curriculum and about half of the calculus curriculum. So when you leave honors pre-cal, you're more than prepared to be successful in calculus if you're lucky enough to take calculus in your next academic term. So this limits deal, I'm going to kind of explain it through examples. So today we're going to look at limits from a graphical perspective. Tomorrow we're going to look at limits from a numerical perspective. And on Wednesday, we're going to look at limits from an analytical perspective. So this week is really all about limits. So let's go ahead and begin. Okay, so again, I'm going to explain this novel concept of a limit through examples. And again, today we're looking at graphs, so we're doing limits from a graphical perspective. So I'm going to loosely define what a limit represents. And for each problem, we're going to find two things. We're going to find the function at the point, which is something you know how to do, and we're going to find the limit for the particular point, which is something you're about to learn how to do. So I want to talk about the limit for a second, and there's a reason I'm finding both these, which you'll find out a little bit later. And I want to show you how this is read. So this is limit notation, and how this is read the limit of f of x as x goes to 2, or the limit of f of x as x approaches 2. And what it wants you to find, it wants you to find a finite value. So it wants you to find a finite value that this function, and by this function f of x, I'm talking about the y value that this function gets what we call arbitrarily close to as x approaches 2 from the left and from the right. So it's pretty technical language, but in essence, this is what you need to do. So in essence, I want to find the limit of f of x. So this is the graph of f of x in red. And basically what you do is and you find it looking for the limit as x approaches 2. So this is 2 right here. So you basically approach 2 from the left and the right. So this red pen is coming from the right. This blue pen is coming from the left. As you get closer and closer to 2, if these pins come together, the y value that they both arrive at is the value of the limit. So the y value that they both come to is right here at 2. So the value of the limit is 2. Now, I want to point out the value of f of 2 and make a certain point. So for f of 2, so here's 2 right here, I'm looking for the closed circle. So f of 2 is up here. This is 2, 3, 4. So f of 2 is actually 4. It's very important to understand that the limit as x approaches 2 does not have to be equal to the value at 2. So the limit, again, when we say the limit, we talk about the value as x approaches 2. So I'm looking at the y value the function gets close to as x is getting closer and closer to 2, not necessarily the value at 2. So clearly here the value at 2 is 4, but the value as x approaches 2 is 2. So technically when we're finding a limit, we're not going all the way to the number that x is approaching. but we're just approaching it. We're getting as close as we can to be able to understand the y value that the function is approaching. And both these values from the left and the right, so my red pen and my blue pen, they must meet in the same place. If they don't meet in the same place, we say the limit does not exist. Okay, let's look at another example. The more examples you see, the more this will bring to heart. So for this example, we're finding the limit of f of x as x goes to 1. Okay, so here's 1 right here. So again, I'm going to approach 1 from the left and the right, staying on the graph of the function. And as I get real close to 1, I look at the y value, and it appears to be 1. So the limit of f of x as x approaches 1 is 1. Now I'm going to look at the value of f of 1. Well, here's 1 here, and the value of f of 1 is, you guessed it, 1 as well. So it is possible for the value at the point to be equal to the limit as x approaches the point. That's very possible, and that's a very special type of situation when that occurs that we're going to cover a little bit later at a later time. Not today. I don't even think this week we're going to cover it, but we're going to cover it a little bit later. I think at the beginning of next week. This special situation, this is a very special situation, like bring out the fancy wine glasses when you see this particular situation. So it's a very special situation where the limit as x approaches the number is equal to the value of the function at that particular number. It's a very special situation that we'll describe and talk about a little bit later. Let's look at our next example. All right, so this next example we're talking about is x approaches 3, and here is 3 here. So again, I take my 2 trusty pens and I approach 3 from the left and the right, and I have a problem here. So in my first indication of a problem for the limit, as I get closer and closer to 3, my pens are not at the same level. They're at 2 different values. It approached 2 different values from the left and the right. When that happens, we say the limit does not exist. So this limit actually does not exist. And in shorthand in math, we say D&E. So D&E abbreviates does not exist. Universally accepted answer for does not exist, that students can use even on the AP exam. All right, so for the limit to exist, when I approach whatever number x is going to, in this case is 3, from the left and the right, my pens should be approaching the same value, but here they're not. Like from the left, the red pen is coming from the left, it's approaching the y value at -2, and the blue pen coming from the right is approaching the y value at -4. So they're approaching 2 different values. In that case, the limit doesn't exist. And this particular case is classified as something that we'll talk about a little bit later. And again, a little bit later, it doesn't mean today. All right, so the limit doesn't exist, but that has no bearing on f of 3. And we can easily find f of 3. So for f of 3, I'm looking for the closed circle. It's located at -4. So f of 3 is -4. Let's look at another example. Okay, so here we're finding the limit as x goes to 4. Here's 4 right here. Okay, so I'm on the graph approaching 4 from the left and the right. And my pins join, so they're coming to the same point, which is very good. And the y value there looks to be 4. So the limit of f of x as x goes to 4 is 4. What is f of 4? Now remember, when we're looking for the value at the point, I'm looking for a closed circle on that particular value. But there is no closed circle. All you have at x equals 4 is an open circle. So that means f of 4 is not defined. So f of 4 is undefined. But you see, it has no bearing on if the limit exists or not. Some people have the false misconception and they think if the value at the point is undefined, that means the limit does not exist. Not true. So what you've been seeing here are two independent operations here. F of the number has no impact of the limit as x goes to the number. These are two independent things. The limit cannot exist and the function at the value could be a number. The function at the value could be undefined and the limit could not exist. The limit cannot exist and the function be undefined. So they're independent of each other. One has no bearing on the other. And so let's look at the last paper example, and then we'll look at a few computerized examples. And we should run through those a little bit faster. It should make a little more sense. And now we're finding the limit as x goes to -2. So here's -2 here. So again, I'm going to put my pins on this graph and get closer and closer to -2. And as I get closer and closer to -2, and I'm actually not on -2 yet. And as I get closer, you see my pins are very far apart. So I think you can see from there, obviously the limit does not exist. And actually what's happening here is there's a vertical asymptote, something I believe you heard of before. And whenever you see a function approach x value, then it could be expressed as a vertical line, and you see the function shoot straight up or shoot straight down, that is an indication of the presence of a vertical asymptote. But when that occurs, of course, the limit doesn't exist. And similarly, I mean, if you look at it, so just understanding what asymptotes mean, it means the graph gets extremely close to that value, but never touches it. So this function is never touching x equals -2. So that means f of -2 doesn't have a value, so it's undefined. So those examples were to kind of explain what limits were and compare and juxtapose the value of the limit to the function at the point. And now we're just going to get some practice. So we're going to look at some computerized examples just to get the practice. Hopefully you kind of have a fairly good understanding of this now. Okay, so I'm just going to run through a few examples. We should be familiar. The limit down here may be difficult to see, so I'm going to read it. This says the limit of f of x as x goes to -1, and this is the graph of f of x. So -1 is right here. So on these problems, I want you to try them first, before I talk about the answer. So if you need a moment, this is the time to pause the video. When you unpause it, I'm going to go ahead and talk about the solution. Okay, so on this particular problem, this is the example when it's going to two different numbers from the left and the right. From the left, it's going up here to 2. From the right, it's going down there to 1, but it's going to two different values. If I had my two pins, they would not be hitting the same mark. So in this case, the limit does not exist. Let's look at the second example. The second example is the same graph, but we're finding a limit as x goes to 1. So here is 1 here. So again, pause the video if you need a little time. I want you to definitely try to find this limit before I talk about it. So pause the video now, and then when you unpause it, I'll talk about the solution. Okay, so if you look at this one, again, from the left and from the right, you should see it's going to 5. So the limit is 5. When finding limits, we don't care about open and closed circles. Open and closed circles in particular are for finding the value of the function at the point. So like f of 1 is 3. That's what makes the closed circle important. In terms of finding a limit, we can care less about an open or closed circle. We don't even put them in consideration. It's just where the function is going to the left and the right, and if it's going to the same place. All right, next problem. So this problem, we're finding the limit of f of x as x goes to 1. There is 1 there. So again, pause the video if you need a little time to figure it out. Okay, so for this one, Again, you should see, again, if I had my pins again, both my pins will be coming to the same place, and the limit would be 5. Now, f of 1, of course, is undefined. There's an open circle and those closed circles. But again, that has no bearing on the existence or value of the limit. The limit is definitely 5. Next example here, we're finding the limit as x goes to 0. And so this is 0 here. Hopefully you understand what you're looking at. Again, pause the video if you need a few moments, and when you unpause it, I'll go ahead and talk about the solution. So on this problem, we have a vertical asymptote. So the graph is never going to touch 0, and it's going in different directions from the left and the right. One side is going to infinity, the other side is going to negative infinity, and so obviously the limit does not exist. And we'll look at 2 more examples. This next one, we're finding a limit as x is going to 3, and I'll use this graph twice on these last problems. So as x is going to 3, that's right here. Let me give you a moment to see what you think the answer is. And you should have said -1. The limit is -1. Of course, f of 3 would have been -2, but the limit is -1. And our last example, same graph, but now we're finding the limit as x goes to -1. And let's see what you think about that. And hopefully you came to the conclusion that the limit does not exist. Again, it's approaching 2 different values from the left and the right. My 2 pins did not come together, so therefore that limit does not exist. So that concludes our lesson on limits. Hopefully you understood this. This is a very important concept. And again, we'll be covering limits for the next few days in different perspectives, one being numerical and the other being analytical. So as we go on in those different perspectives, you're going to get a better understanding of limits. But that concludes this particular lesson on limits from a graphical perspective, and we'll see you next time.